Okay, hello everyone and welcome back to your YouTube channel and welcome to this very interesting video today. As you must be aware, some of my master students, they are taking classes, a specific module about advanced power systems, power system dynamic, electromechanical processes in electrical power systems and so on. All of them are working with near to real power systems. We are talking about networks with a large size, and those networks they impose several challenges. Okay, we are talking here about classical electrical power systems dominated by synchronous generator. That is perfectly fine, but we are talking about large power systems. Okay. In that case, of course, the equations are still valid. But the issue is that performing calculations using by hand or manual calculations in a very large power system, that is an issue. And that is the reason that we are using power system analysis software, what we call computer-aided engineering, basically. We are using commercial power system analysis. And in this case, I am using my favorite one for power system analysis for electromechanical processes, the DIgSILENT power factory, okay? If you are following my channel, you must know that there are several previous videos. This is probably one of the at the top, because I will be talking about time domain analysis using DIgSILENT power factory. Okay, this is a very important topic. However, I must clarify here and from the very beginning. Okay, this is a basic video. Okay, this is not a course. This is not a training. If you want to learn a lot about time domain analysis, that could be weeks working in this topic. Okay. A training of this can be several days, and we can go deeper and explain equations and so on, okay? At this stage, what I will do is just show a general overview and the basic terms and the basic steps that anyone that is not top expert will require for perform time domain analysis by using the DIgSILENT power factory, okay? But before we start the session today, remember to subscribe to my ResearchGate. Over there you will find many of my papers, presentations, and so on. And also you can find papers, documentation, scientific documents from many scientists. Okay, it's a social media for scientists. It's a very good resource of information. For now, it's free. Okay, take the opportunity, subscribe, use your access, and get very good set of documentations over there. Also, this specific video is connected with some practical examples. For that reason, you can go to my GitHub and you can download from there. The examples that I have been using in the previous videos regarding initial conditions and so on, and also some other videos in the future. If you are here, it's because you are in my YouTube channel, and as consequence, I highly suggest that if you have the opportunity and you are interested, subscribe to my YouTube channel, okay? Finally, if you're interested on know what we are doing, the cutting-edge research and the most recent advances in electrical power system, I highly suggest that you subscribe to my social media. We have Twitter, we have LinkedIn, okay? Well, but it's time to talk about a short introduction about modeling and simulation of electrical power systems, okay? My students, they already took a couple classes about modeling and simulation of electrical power systems. However, here is just a basic introduction, okay? What you need to understand is that every single dynamic system, any single dynamic system, it could be finance, it could be biologic, or could be any kind of dynamic system, can be modeled by using a set of differential equations and algebraic equations, okay? that set of equations together receive the name differential algebraic equation model, okay? That is the differential and algebraic equation model, okay? That is the proper name that we use. And basically it's because we have a set of differential equations. You can see here x is the vector. This is the state vector, okay? But this case, the dot on the top represent that this is the first derivative of the state variables, okay? And here there are another set of equations. Those equations are representing the output variables, and that is for the representation of the algebraic equations, okay? For instance, in the specific case, very simplified case of a power system, differential equations include dynamics. One of the important dynamics that we are taking care in this course is basically the swing equation, okay? Regarding algebraic equation, there are many algebraic equations inside the power system, but probably the most known is the equation representing the network and the behavior of the network in a steady state, fundamental frequency, the load flow, okay? Now, when we are studying the transient or the dynamic processes inside the electrical power system, we need to solve the differential algebraic equation model, okay? We need to solve that. And to be honest, in the literature, there are several approaches that can be used to solving the system of differential algebraic equations, okay? There are many methods, but all of them have something in common, okay? Depending on the numerical methods and the modeling details, some approaches can be used, okay? However, if we classify all the methods available for solving the system of differential algebraic equations, the set of differential algebraic equations, we can identify that there are two most used approaches, okay? We can say that there is something called simultaneous implicit method, and I discussed this before. This is one approach where the differential equation is approximated by any kind of technique. For instance, it could be trapezoidal rule, or it can be Simpson rule, etc. But at the same time, you are simplifying the differential equation and transforming it into an algebraic equation that they can be combined with the traditional equations, algebraic equation, and solving all as single step, okay? That is one of the approaches. But the second approach is probably the most used method, okay? The most used method is the partitioning explicit method. We talk about this method many times in classes. However, the partitioning explicit method is something extremely simple, okay? We already have very good methods and very good algorithms to solve the network equations, for instance, the load flow. We have very good numerical techniques to solve differential equations, for instance, Runge-Kutta, predictor corrector, and so on. Well, this partition explicit, what it's doing is solving the differential equation, then solve the network equation, and again, and again, and again. What I am telling you is that we are solving at the same time, the differential equation, the differential equations, and then we solve the network equation. But we are doing this for each integration step. That is what is happening, okay? Well, we already discussed about the theory behind solving the differential algebraic method, and I say that the partitioning explicit method is the most used method for solving the differential algebraic equations, okay? And if you look software, commercial software like PSSE or Powerwall or DIgSILENT Power Factory, all of them, they use this approach, okay? And in this section, I will talk about transient analysis using DIgSILENT Power Factory, okay? From here and until the end of this video, I will be talking specifically about time domain processes, time domain simulations using DIgSILENT Power Factory, specifically for the problem of dynamic processes in the electromechanical time scale, okay? And now what you can see here is I will be running my discussion in this video using the two possible versions, typical versions that people use for DIgSILENT Power Factory, okay? The most recent version at this moment that we are creating this video, this is the version 2021 service pack number 1, okay? If you go to DIgSILENT Power Factory service pack number 1, version 2021, you will find that there is an icon on the top at the toolbox that you will find a set of calculation functions called simulation, RMS, and AMT, okay? You will later identify that the icons are very different compared with the oldest version, okay? On the left-hand side here, I have the menu. It's the same menu. It's the same menu that you will find in the oldest version, okay? And also you have the more colorful icons that they used to use in the very old version, okay? I am making this distinction between the new version of Power Factory and the old version of Power Factory because some people around the world, they still using versions like 2019 or 2018 version of Power Factory, and the icons still look similar to this, okay? But coming back to my explanation, Power Factory is a very powerful software for power system analysis. To be honest, Power Factory has been equipped with several calculation functions, and you are able to run numerical simulations like load flow, short circuit, etc., etc., etc. And depending on the level of detail, you can control what you are doing inside the software, okay? DIgSILENT Power Factory have the possibility of providing a very wide set of possible calculation functions, okay? However, in this course, in this video in particular, I will be talking about the simulation RMS and the simulation EMT, okay? EMT, before somebody asks me, remember my classes about time scales. EMT is the name that we use to refer for electromagnetic transients. Electromagnetic transients, they are probably the fastest transient that you can find in the electrical power systems, like for instance, lightning strikes, okay? And one of the characteristics of this kind of simulation is that we are using instantaneous values. I mean, when you run this simulation, the values that you will get for voltage or currents, they are instantaneous values. If you are solving a transient using a sine wave form, as typical in an AC system, well, the solution that you will get, it will be another sine wave where every single point is defined by the instantaneous value, okay? But the interesting thing is that Power Factory has been extremely powerful, okay? Power Factory has the possibility, if you remember my discussion about time scales, Power Factory has the possibility of running different kind of simulation, okay? Power Factory is able to run calculation simulation for very short term, as I defined very early in this course, a very short term time scale, and that is for electromagnetic transients, to be honest. With this kind of simulation, you can obtain the instantaneous values, you can get the instantaneous value and make studies for very short time period, okay? And then also Power Factory have the possibility of running simulations, the simulations that I am interested in this course, midterm simulations. We are talking about the classical electromechanical transients, okay? If you remember my class about time scale, you must remember that the midterm electromechanical transient for classical electrical power system, for synchronous machine dominated power system, we are talking about a frequency range between 0.1 hertz to 10 hertz, okay? That is related with the classical time constant of the synchronous machine between 10 seconds to 100 milliseconds, okay? We are talking about here fundamental frequency 50 hertz. But also Power Factory allow you to run calculations for long term, okay? For instance, Power Factory is equipped with a functionality that is called quasi-dynamic simulation. Not much people is using or aware. However, since I published a video, I think like 6 months ago, more people are using this functionality and taking over. I am really proud, I'm really happy about that people start to use quasi-dynamic functionality, okay? Well, Power Factory is able to run simulations in the 3 different time scales, short-term, mid-term, and long-term. However, in this course, I will be focusing specifically in mid-term transient, okay? Specifically in electromechanical transient, okay? If we are talking about this kind of mid-term, short-term simulations, Power Factory is equipped with several calculation methods, okay? The calculation method that Power Factory is able to use is basically, it's basically 3 types of simulation functions, okay? All of them are inside the short term and the mid term, okay? What I want to explain is that the functionality for simulations RMS and AMT inside Power Factory, they have basically 3 calculation methods. The first one is the symmetrical steady-state network model. In that case, we are solving the dynamic, the power system dynamic, but the consideration is that we are using a system where there is only fundamental frequency. I mean, for instance, in Europe, 50 Hertz. And if there is only fundamental frequency and we are not considering the transient of the transmission network, for instance, we can use the concept of phasor, okay? Because we are using the concept of phasor, every single variable, electrical variable, is represented by the RMS value. And that is the reason, that is the reason that Power Factory called this functionality RMS. Because in this case, all the electrical variable, voltages, current, etc., we can make a plot over the time, but what we will plot is basically the RMS value of the current or the RMS value of the voltage, okay? Then we have, for instance, the 3-phase for steady state. We have the possibility of simulating conditions where the network is under asymmetrical conditions, okay? When I was talking about this symmetrical steady state, we are using fundamental frequency, but at the same time only positive sequence, okay? That means that one of the limitations of the first step is that we can run only balanced and symmetrical conditions, okay? If you want to study a short circuit, 3-phase short circuit, you can use the symmetrical steady state model network. But if you have the possibility, or you have to run a simulation considering some asymmetrical condition, for instance, a single line to ground fault, you need to use the second approach, and that is the 3-phase for a steady state network model. In that case, you can use positive, negative, and zero sequence model to represent the network, and you are able to calculate asymmetrical conditions, okay? And finally, the third simulation function that we have inside Power Factory is basically the electromagnetic transient. Electromagnetic transient is used for this kind of very short-term simulation using instantaneous values, okay? Using instantaneous values. And that we will discuss each one of them later, step by step. Well, if you remember my explanation of initial conditions calculation using DIgSILENT Power Factory, you must know that there is a very specific functionality to do so inside Power Factory, okay? If you are using the new version of DIgSILENT Power Factory, you must recognize this window. When you open the window, you will realize that there is a top section saying simulation method. And then you have here, below that, you have something called network representation, okay? And it's similar. If you are using the old version of Power Factory, you will have something, a section for simulation method and a section for network representation. What I'm telling you is that when you are using the command initial condition, and that is the name command initial conditions, when you run this icon here that is located here at the very top, when you run the command initial conditions, this window will open, okay? And this configuration over here, simulation method and network representation, they are basically used to define the 3 different simulation functions available. I mean, if you select here RMS values, that means that you are running the classical electromechanical transients. That means that you are considering fundamental frequency. You are using fundamental frequency, that is RMS value for every single electrical variable, voltages, currents, and so on. And here you have the possibility of using 2 possible network representation. If you use the first option, balanced positive sequence, that is the case number 1 here, okay? When you are interested only on positive sequence, that means, for instance, 3-phase short circuits. That is the case of running RMS values, using electromechanical transients, and using balanced positive sequence network, okay? The second option here is the 3-phase for steady state network model, okay? You can keep the option number 1 here at the very top, simulation method equal to RMS values, and that is for the electromechanical transients, okay? The classical electromechanical transient like power angle stability, for instance. But because you are interested in the power system behavior during a asymmetrical fault, well, in those cases, you can select here the network representation, and that network representation could be using unbalance, okay? And in that case, Power Factory will give you results in A, B, C. I mean, you will be able to receive results for voltage in A, B, and C, okay? Finally, the last option here is running an electromagnetic transient. That could be the case, for instance, if you are calculating the inrush current using the instantaneous values. If you are interested in inrush current, you can run an electromagnetic transient simulation. In such case, you need to select here the simulation method in instantaneous values. And when you do so, you will see this later, but when you select instantaneous values, the DIgSILENT Power Factory automatically select unbalanced 3-phase representation. And that is because when you are using instantaneous values, you are using the full model. You are using the most detailed representation of the power system, the components, and so on, and that is 3-phase representation, okay? Well, this is just to tell you that you have the possibility of selecting this kind of combination, simulation method and network representation.